The potential of getting a supercapacitor that is on par with lithium-ion means that we have a much cheaper source, a green, easy-to-produce source of energy storage. Lithium-ion batteries are not particularly easy to work with, and the lithium-ion itself can be poisonous in cases. And then you have disposal issues, and you have lots of issues with thermal management, of thermal runaway. There's all these issues that will be solved by coming up with a supercapacitor that is on par or better than a lithium-ion battery.
Our project is focusing on creating a renewable energy storage solution that uses some low-tech materials that are non-toxic, and basically anybody with some moderate chemistry knowledge can be able to put this thing together. We want to create an alternative to things like lead-acid batteries or lithium-ion batteries with something that has a higher energy storage capacity and that's made of materials that are more renewable.
Ted is a very generous man. He was interested in this project for a while now, and he basically contacted us, chemistry students, see if you're interested in this, and the ones who got the message, we came in here and then we started from that.
Well, I don't have a background in chemistry, and my background wasn't engineering, although I was always very interested in engineering. My schooling was a variety of things, but I ended up wanting to go into international trade and international business. Then later I got involved in venture capital and angel investing, and I became the manager of the Monterey County chapter of the International Angel Investor Institute. So I did some investing and did okay, and so I retired kind of early, and I started to research energy storage, which arguably is the most important issue of sustainability. I just wanted to get involved, and I figured if I could come to UC Santa Cruz and bring some of the research that I have found, looking for a way for us to build a supercapacitor. In our case, what we wanted to do was to build a supercapacitor that anybody could build in their kitchen. So I made contact with UC Santa Cruz, showed them my research, told them my idea, and started to work with the Ideas group.
Basically, the project was trying to use graphene nanostructures to improve the supercapacitive capabilities of manganese oxide, which is known to be a good supercapacitor material. And from there, Ted did a little more research, found simple ways to synthesize these graphene nanostructures, and then from there, the graphene supercapacitor project emerged.
One of the most interesting aspects of our project is the materials that we use, specifically graphene, or graphene oxide. It's kind of this new wonder material that's only recently been talked about. I mean, it's only been known for a couple of years now. Just got a Nobel Prize a couple years ago for a guy who made graphene by taking off pieces of graphene from graphite using Scotch tape. It seems kind of low tech, but I think it kind of talks about how amazing this material is.
All graphene is a rock of graphite whittled down into layers. And if you whittle it down to, let's say, 7 layers or less, then it's called graphene. And it's put into flakes, and it creates a surface where you have the ability of it to carry electricity lightning fast. It's unbelievable. It's also the hardest substance in the world, harder than diamonds.
So we have 5 test tubes, each with different chemicals. One has graphene oxide, one has manganese sulfate. 2 of them have washes. We rinse it with deionized water, and the other one has sodium hydroxide. Basically, we dip a stainless steel substrate into each one of them. That way we can stack layers of each chemical onto each other, and each cycle takes about 4.5 minutes. So we do that 100 times to have 100 layers of each chemical.
The goal of all of these dippings and dryings of this with this steel substrate, this steel bar basically, or plate, is just to generate one of the electrodes that are going to be required for the supercapacitor, right? So you're going to have one electrode and another electrode basically dipped into electrolyte solution and allow a circuit to be generated, basically to allow charge to move from one side to the other, and eventually you'll get work out of that. In a nutshell, it sounds simple, and that's because it is simple. We wanted something that was really low tech, as I said before, and something that someone can do in their garage. We don't want to have to require people to need an advanced chemistry laboratory or a PhD to run it for them. So this is the simplest as you can get.
Basically, you sweep the voltage applied to the electrode that's made of your material, and you see the current response that emerges from it. And based on that current response, you can get a value for the total capacitance of your material. But from that analysis, from that response, you can essentially quantify how good your material is at being a supercapacitor. So basically we tried this first cyclic fault tolerant experiment, didn't work out. Tensiostat said it was overloading, that means there's too much current running through. Quite easily explained by the fact that our counter electrode has been soldered together with tin before. It snapped, it's a snap platinum electrode. I had a feeling this would happen, and that kind of confirmed it. I'm gonna have to go get a new, clean, and unbroken electrode, and we can try this again. I'm sure it'll work out better this time.
We ended up with what we consider success, and that is to replicate the key component of the supercapacitor. We're now at a stage we've got to improve our graphene production, make it cheaper and quicker and easier, and once we've done that, the door is open for anybody to create a phenomenal supercapacitor.
We discovered that the supercapacitive capabilities of the manganese oxide material that was originally used was improved beyond what was found with just graphene oxide precursors, like commercially available graphene. And that just pretty much opens the door, like, wow, we don't need to have all these crazy instruments, these $1 million like labs to make something that is like the next leading material in the world as far as, well, not just energy for anything. Graphene is like the new hot material, probably be incorporated in almost every technological device in the near future. And like I said, that can be made essentially at home. You can make things in a sustainable manner that are technologically relevant. Like graphene, that's like the new hot material, probably of our generation maybe. We've got to find new ways of making this that aren't inaccessible to the greater population.
There's enough people out there, I'm dealing with them right now, of building their own electric cars and building their own batteries and supercapacitor. You look on YouTube and you can see them doing it. And that just could be the breakthrough. Who knows? Let's find out. That's what we're about. Let's find out and make it available to everybody.